Through exploring our data, we realize that longitude has nonlinear behavior with respect to the median income. So using this single variable for linear regression isn't going to work out so well. But let's go ahead and use a nonlinear model. Let's go ahead and use decision trees. Now we're going to have a whole set of series of lectures devoted to decision trees and models based upon decision trees. But at this point, let's just initially talk about it, gain some understanding, because we're going to use decision trees to illustrate a key concept of machine learning. So decision trees are non-parametric models using a binary tree structure. I'm going to run this code here. I'm going to explain what's going on in a bit, but I'm going to run this here to visualize our decision tree model. So here is our decision tree model. One thing you'll realize is that it has a tree-like structure, an upside-down tree, hence its name. What we have here is called the root node of our tree at the very top of this upside-down tree. And what decision tree is going to do is going to ask a series of yes or no questions, in other words, true or false, to bin points into leaves or nodes. So these right here are called nodes. So let's take a look at the very top of our tree, the root node. I want to point out some fields of interest. So we have here samples, tells us all the number of samples that reside in this node. And what the decision tree model is going to do is going to best separate our points. We want similar points to be in this space and other similar points to be in this other space. And it's going to choose this splitting point. And the splitting point, you can view it as a question, a yes or no question, a question that has a true or false answer. Since we only have longitude, it's only going to make questions based upon longitude. Only using one feature for this example here. And it said, okay, all the points that are less than this value here of longitude, go ahead and move to this bin. And if this is false for you, if this is not true for you for those observations, move to this other bin here. So it's going to separate our points into two bins based upon this question it decided to ask. Now we're not going to go into how the model decided that this was the best question to ask. We'll discuss that for future lectures, but let's just go ahead and just focus on it picked a question that's going to ask for all our observations. So we separated our points into two bins, and the process repeats. At this bin here, let's go ahead and apply the same process. What is the best question to ask to best separate my points? And then it further splits the data. So if we look at here, those are close to about 5,000 samples in this bin, and over close to 16,000 samples here. So we sum these up, we go ahead and have this number here. So it further splits, and at this branch it applies the same process. It's going to figure out what's the best question to ask to best separate the points in this bin here. And the tree grows until it reaches some sort of termination criteria. These nodes here, since they're at the very end of our tree, they're going to call the terminal nodes, sometimes called leaves. These are the leaves of our decision tree. Now you might be wondering, what prevented our tree to keep on growing? Because if we look at these terminal bins, these leaves here, there are still samples that reside in this leaf. There's still samples here, 640. So we could have split further. We could have further split this bin node. But what prevented the tree from keep on growing was that there was a hyperparameter called max depth. In this situation, we set this max depth equal to 2. So this is going to govern how the tree grows. It's going to prevent it from growing any further. We're going to play around, explore this hyperparameter later on. But this essentially prevents our tree from growing. Now I say it's called a hyperparameter because we set it prior to learning. We set it prior to using the fit method of the model. And it's going to govern the learning process. It's going to govern the resulting model parameters. With linear regression, the model parameters were those beta coefficients associated with each of our features. But in decision trees, the model parameters are the bins, the location of the bins, as well as the question that was asked to create that bin. Other thing I want to point out with here with decision tree is that with linear regression, we had a function that was sort of a more traditional mathematical function. We saw f of x is equal to beta naught plus beta 1 times x of 1 plus beta 2 times x of 2 and so forth. With decision trees, a little more abstract. We don't have this nice functional form. So with machine learning models, we're not restricted to some closed form equation for our model. We can have something abstract like this, like a set of yes or no questions you're going to ask to best separate the data. The value here for each bin represents the mean value for all the observations in this bin. Now, once you constructed this decision tree model, you might be wondering, okay, how does the model work to make predictions? During the training process, it's going to best separate the training observations into these bins, into these terminal leaves. It's going to stop, given the max depth that we set for the model. To make predictions, we start at the root of the tree, and we're going to ask these sets of yes or no questions. And we're going to ask these sets of yes or no questions to see where does our observation, which bin, which terminal node, what leaf does this observation going to fall into. So we start an observation and we want to know the predictive value. We want to make a prediction on that observation. We start here. We answer this question. Is this true or false? If it's true, move to this bin. If it's false, move to this other branch. And repeat the process until our observation resides in this terminal node, in this leaf. And let's say our observation resides in this leaf here. Then the value we predict is this value reported here. 2.625, which was the mean value for all the observations, all the train observations that made up this leaf. So since we have 4 leaves, 4 terminal nodes, how many distinct values will this model predict? We have 4 leaves, 4 buckets, 4 bins at the very end. How many distinct values will our model predict? It's going to predict 4 distinct values because there's only 4 bins. Let's go ahead and look at the code used to generate this graph here, and I'll point some things out. So we're going to import the decision tree. So we're going to import this module called tree. Within there we have various tree-based models. The one we're going to focus on here is the simple decision tree regressor. There is a classification version. There are other machine learning models that are based upon decision trees. We'll talk about those further in a future lecture, but let's go ahead and look at the decision tree regressor. And notice here we're going to set the keyword argument max depth equal to 2. This max depth is a hyperparameter for the model. We're going to fit the model only using the longitude feature, just for illustrative purposes. In real life, you'd use all the features available to you. Let's go ahead and visualize our data. And let's go ahead and visualize the predicted values of our model. So we're going to use our trained model, we call fit, to make predictions. Remember, during the fit method, when we call the fit method, it's constructing this tree model. It's figuring out what are the best questions to ask. Something we also do here, I want to point out, is we're going to use this package here called GraphViz. And this is a nice package we can use to visualize our decision tree model. A nice thing about decision trees is that you can easily visualize how the model works. Here's how the model works. You can show it to someone, say, hey, this is how we make predictions. You just follow these sets of yes or no questions to see where your observation lies in. So the nice thing about decision tree models is that they have high explicability. It's easy to explain to someone or understand how it's making predictions. It's less of a black box. Some other models are more black boxes, so it's hard to understand how it's making predictions. So that's a nice pro for decision trees. So let's focus on this figure here. So So y-axis is the value we're trying to predict, and x-axis is the single feature we're using for our analysis. And drawn in red is the predicted values of the model. And notice here, there is only 4 values the model predicts, which makes sense because we discussed that since we only have a max depth of 2, we only have 4 bins. We only have 4 terminal nodes, 4 leaves in the model. And some observations were binned into this bucket here. So it's hard to see, but it looks like it's about 1.5, and that corresponds to this bin here. And there's another set of values that reside in this bin. It's about 2.6. Yeah, that corresponds to this bin here. And then the observations that lie in this region, those are in this other bin, so close to 1.4. And then we have the final 4th bin, values of 2.2. Now, looking how well our model performed, do you guys think this model did a pretty good job of fitting the data? What do you guys think? I would argue did a pretty poor job. There's only 4 distinct values. Looks like all these high values here doesn't really predict pretty well. So it does a pretty poor job. And you might be wondering, okay, how can we go ahead and increase this model's performance? How we can go ahead and make this model perform better? So one way we can make this model perform better is by playing around with the max depth. Max depth is a hyperparameter. You can think of our model as a machine that has all these knobs and whistles, and we set these knobs and whistles prior to pushing in data, prior to fitting in data with the labels so it can learn from. So maybe if we can crank up max depth, say, hey, tree, be bigger, be more adaptive. Perhaps we can have a model that's going to work better, perform better, and fit the data better. But there might be some consequences if we play around with this max depth a little too much.